Okay, to start off chapter 20, let's go through a couple common reactions you're going to see in regarding amines and amides. Okay, so some general reactions. First of all, let's define what an amine is and what an amide is. An amide looks like this, where on a carbon you have a double bond O and an NH2 or an NHCH3. As long as it's nitrogen and then that nitrogen is attached to carbons or hydrogens, that will be an amide. An amine is the simpler version. It has no double bond O, it's just nitrogen with some number of carbons or hydrogens on it. Okay, so this is an amine, and this is an amide. Now, I'm going to start by talking about a couple reactions that let you make amides because they'll be helpful in synthesis problems and things like that. So there are two main ways we have of making the amide. Let's say I want to make this. I kind of erased it, but let's redraw it. NH2 with a methyl. How do I make this? Or how do I make an amide, right? Well, the first reaction that you have an option of using is have a carbonyl with a good leaving group on it and have that carbonyl attacked by the nitrogen group you want to add. If it's NH2, you add one hydrogen to that. So I want NH3 to attack this molecule. If it was a nitrogen with one hydrogen and a CH3, then I'd want this to be one hydrogen more than that, so NH2, and that nitrogen would have a CH3 on it. Either way, the way this reaction works is the nitrogen with its lone pair will attack the carbonyl, and this will swing up, and you will get this intermediate. O minus because the electrons swing up to the oxygen, the chlorine and the methyl are still there. And now we have the nitrogen that did the attack. That nitrogen had two hydrogens and a CH3 on it. As always, that O minus is going to look to swing back down. And now it can either kick out the nitrogen, which is positive, but that will just undo what we're trying to form, so we're not going to do that. We're going to kick out the other good leaving group, the chlorine. Chlorine gets kicked out, and now you have C double bond O, the methyl, the nitrogen that you added, but it still has those two hydrogens on it, and a CH3. So this nitrogen is positive, all you have to do is deprotonate it. So pull off pull off a hydrogen, put the electrons onto the nitrogen, and there you go. So this is one way of making a amide. And how do we make this? The carbonyl with the chlorine on it? You can make that from carboxylic acid. So let's erase this. If you want to make this, you can make that from carboxylic acid, which is a C double bond O, OH, by using SOCl2. Like we said before, if I want to replace that and turn it into an amide, I just need the corresponding nitrogen over it with one extra hydrogen. So NH3, and this would be NH2. Okay? Now there's another way to make amides, and it also involves starting from carboxylic acid. But while this is two steps, this method goes straight from the carboxylic acid to the amide. And that reaction is still the amine that you want to add. So I want it to be NH2, so I'm going to have one hydrogen more over the arrow, so NH3. But you need one other thing, and that thing is something called DCC. Now, you don't have to worry about the mechanism of DCC. All you need to know is what DCC does is it reacts with carboxylic acid. More specifically, it takes this OH group right here and makes it a really good leaving group, just like the chlorine is over here. So basically DCC couples with that oxygen and it gets kicked out when the NH3 comes into attack. And again, you don't have to worry about the mechanism. But these are your two go-to methods of making an amide. Carboxylic acid with SOCl2 to make an acyl halide, or acyl chloride in this case, and then your nitrogen attacks that. Or carboxylic acid with the amine group you want to add, and DCC. Okay? Now, let's talk a little more about amides because there's an important rule you should know about that, and it involves what does LiAlH4 do to it. So, let's draw out that amide again. NH2. We call this a primary amide because the nitrogen is only attached to one other carbon, so primary amide. And then of course we have secondary amides where it's N with one hydrogen and two carbons attached, so secondary. And we have tertiary amides where the nitrogen, if you can guess it, is connected to three carbons, like that. Okay? Now, all three of these follow the same exact rule when you react them with LiAlH4, an old reducing agent from exam 2 and even Orgo 1. And I don't think you have to worry about the mechanism of this, and quite frankly, I'm not too familiar with it. All you need to know is, let's say this is carbon 1, 2, and 3, well, nitrogen being 3. What you're going to do is whenever you have an amide reacting with LiAlH4, what ends up happening is the double bond O disappears. So you would end up getting this. Still the same number of carbons, 1 and 2, and then nitrogen 3, but now that double bond O has disappeared. And the same can be done for secondary and tertiary. There's no extra rule about it. So LiAlH4 will turn this into that with the methyl, and tertiary amine would turn into N with two methyls. Okay? So LiAlH4 will turn amides, whether they're primary, secondary, or tertiary, into amines. Okay? LiAlH4 does a couple other things in this chapter too. Namely, it can reduce N3 and C triple bond N both into NH2. So for example, we have, let's say C triple bond N, and we have N3. Okay? So I'm going to draw out what N3 looks like because you're going to see it a couple times in this chapter. It's a nitrogen single bonded to another nitrogen and another nitrogen after that, so three nitrogens. The two on the end have a triple bond between them. The nitrogen in the middle is positive, and the nitrogen on the carbon you're attached to is negative. You will also sometimes see the resonance form of N3. And what that looks like is the negative charged nitrogen can swing down like this, and the electrons over here on the triple bond move to the nitrogen on the end. And so the resonance structure would look like this. N double bond, N double bond, N. Nitrogen in the middle is still positive because in general when you see nitrogen with 4 bonds it's positive. And if you see a nitrogen with 2 bonds, typically it's negative. 3 bonds is where it's neutral. Okay? So one way or another, this is what N3 will look like. But either way, what does LiAlH4 do to these structures? With the C triple bond N, I'm not going to draw out the mechanism. I don't think you're expected to know it, but you should know what you get. If I number this carbon 1, 2, 3, and we'll number the nitrogen 4, LiAlH4 will reduce that triple bond to a single bond, giving you C, well, let's not draw out the carbon, 2, and then NH2. C triple bond N gets reduced to C single bond NH2. And if I do my numbering, here's 1, 2, carbon 3, nitrogen 4. Okay? Same deal for N3. When you treat this with LiAlH4, whether it's this resonance structure or the other, it doesn't matter. So I treat this with LiAlH4, and what I can expect to get is carbon 1, carbon 2. Only the nitrogen directly attached to the carbon is the nitrogen that stays. Okay? So in this case, we would get N2, nitrogen, NH2. Okay? So I have carbon 1, carbon 2, and then nitrogen 3, which was directly attached to carbon 2. The other two nitrogens will be released as nitrogen gas, as N2 gas. Or if I drew that out, N triple bond N. Okay? We'll be seeing that N2 positive is a very good leaving group in a number of mechanisms coming up. But for now, don't worry about it too much. We'll see it in future videos. Now, caught it. when are we going to use N3? When are we going to use C111N? A very important point to make is, let's say I have a carbon chain. One second, I need a new top marker. Okay, so let's say I have a carbon chain with a leaving group like this, Br. And I'm going to have a second carbon chain just like it, Br, and I'm going to react it with two different things. One thing I'll react it with is NaCN. The other thing I'll react it with is KN3. Okay? So let's start by identifying what's going to happen in the first place. So we have a carbon with a good leaving group. That's nothing new. Bromine loves to leave, which means the carbon it's attached to loves to be attacked. So we know at the very least this is going to be one arrow. The leaving group is going to want to leave and take its electrons. Okay? That would leave this carbon or this carbon positive, so something wants to attack it. Who is going to do the attack? Well, remember, whether it's sodium, whether it's potassium, those are metals. And metals are always positive when associated with nonmetals like nitrogen or carbon. And if the nitrogen or the potassium are positive, that means the thing they're attached to is negative. So the carbon of the CN is negative, the nitrogen in this is negative, and they want to attack things. So, who does the attack? In this case, the N3 attacks this carbon. In this case, the carbon attacks this carbon. And what you end up getting is 1, 2, and then the bromine is replaced by your nucleophile. In this case, the CN, and in the bottom case, it is replaced by the N3. Okay? Now we're going to treat both of these with LiAlH4. Okay? What would I get if I treated this with LiAlH4? Well, we said we would get NH2. But this is the key difference between doing a nucleophilic addition with CN and N3. N3 is just nitrogens, but CN has a carbon in it. By doing this, you are adding a carbon. So if I count this, I'm starting with 1, 2 carbons in both of these structures. And here I'm adding a third. So I have 1, 2, 3, and then this carbon 3 must be where my NH2 goes for the CN. In the case of N3, when that reacts with LiAlH4, I only have 1, 2 carbons still, which means I should have 1, 2, and then NH2. So very commonly in multiple choice questions, they'll ask you, if I give you these reactants, which will give me this product that I'm looking for? And often they'll give you CN versus KN3, or N3, and you have to decide, do I want to add a carbon, or do I want to keep the carbon count the same? So be wary of that trick. There's one other thing to point out involving these carbons with good leaving groups on them, and that is, what if it isn't N3 or CN? What if it's just NH2 or something, like what we were doing to make our amides? So, let's say I still have that same good leaving group, and I have, let's say, NH2CH3. Okay? Well, what we just did doesn't change anything. Nitrogen has lone pairs and it likes to attack a carbon, and this carbon has a good leaving group, so it'll definitely want to attack there, just like before. But here's the important rule you need to know about nitrogen. It is really good at reacting. And that means even after that nitrogen adds to that carbon, let's say this is what we have, CH3, H, and then whatever base, let's say it's the Br minus, comes in and pulls off the proton to neutralize that nitrogen. So we have this right now. All we did was have the nitrogen attack that carbon, kick out the leaving group. So we have 1, 2, 1, 2, and then the nitrogen. The important rule to know about nitrogen is it doesn't stop. It will keep reacting with these carbons with leaving groups unless we tell you there's only one. And usually we don't, so don't assume there is only one. This reaction will keep going until nitrogen has no more room for carbon. So what I mean by that is you're going to end up doing the exact same thing a second time. You have NH2, you have the CH3, or sorry, what am I doing? You have the carbon with the leaving group on it. And so that nitrogen will end up attacking the carbon with the leaving group a second time, taking out the leaving group. And now I have NCH3 with the hydrogen, and now it added the other 2 carbons and the 2 carbons it added previously. So now I have 1, 2, and I have a second set of 1, 2. That nitrogen is positive, and again, the Br minus will deprotonate this. Electrons go to the nitrogen to neutralize it, and I'll have this. But guess what? It still has a lone pair, so it's not even done then. It's going to add a third time, which means one more time that nitrogen will attack the carbon with the leaving group on it. Kick it out, and we'll be left with this as our final product. N, 1, 2, 1, 2, 1, 2, and the CH3 that it had originally, nitrogen being positive. Nitrogen will keep adding until it has no electrons left. It'll remove hydrogens if it has to, but it will keep adding until there are no hydrogens left and nothing but carbons. So another example of this polyalkylation concept where you're adding multiple carbons to a nitrogen. Let's say we have a bromine attached to a carbon chain of 3. So 3 carbons and a bromine. Well, you can try and do the mechanism on your own based on what we just did, but what you should expect to get is a nitrogen that every single hydrogen is replaced by this carbon chain. So a nitrogen with 1, 2, 3, 1, 2, 3, 1, 2, 3, and then it will add a 4th time, making that nitrogen positive. So again, 1, 2, 3, and positive. This should be what you expect to get. Okay? And if you want to see more of this, well, we're going to be doing this again when we get to the reaction called the Hofmann elimination. Okay? So that'll be in a future video. Now, there's one other reaction worth mentioning, and that is H2 with nickel. That's the other weird one you're going to see, but there's nothing too special about it. H2, nickel. Now, the way they write this will be different. They have a couple ways of writing it. They'll either write H2 with nickel, or they'll write H2 with rainy nickel, or they'll write no H2 but rainy nickel, or sometimes they're just going to write H2 and catalyst. Whatever it is, you've seen H2 before. It's something that turns double bonds into single bonds, and sometimes even triple bonds. So what you can expect is if you have C triple bond N, or if you have N3, kind of just like what we did with LiAlH4, it's going to turn that into an NH2 with whatever number of carbons there are attached. If this N3 had 1 CH3, then it is CH3 with an NH2 attached. If this is C triple bond N, and let's say there's a hydrogen on that, then it becomes CH3 NH2. Okay? It just adds hydrogens until every side is neutral and single bonded. Another example you'll see it sometimes is if you have a benzene ring, and on that benzene ring there is NO2. For the record, NO2 looks like this, a nitrogen with a double bond O and an O minus on it. And then there's that bond to the benzene. And that also ends up becoming NH2 when treated with H2 rainy nickel. So, NH2. Okay? So there's a whole lot of NH2 made by this, but it can reduce other things too, like carbon-carbon double bonds, I believe. But those are the most common examples you'll see it in this chapter.